Welcome to Physics in Films. Armageddon, saving Earth the Hollywood way and failing. If this is your first time visiting this channel, the videos in the Physics in Film series are motivated by the work of the Hollywood directors. Each video is dedicated to a Fermi problem based on the scientific plot, or part of the plot, shown in one of the blockbuster Hollywood movies. Today's cinematographic Fermi problem will be based on the 1998 movie Armageddon. In fact, this video is an abridged version of a longer video. The original video contains additional comments on Hollywood science versus real science, astronaut selection and training, astronaut walking on the moon, and a companion Fermi problem. In the movie, a large asteroid is in collision course with Earth. NASA decides to send a team of drillers on the asteroid whose task is to drill a hole on the asteroid, place a nuclear bomb in it, and finally detonate the bomb. After the detonation, the asteroid splits in two fragments which miss Earth. How good is NASA's plan? First, let me present some quantitative information as reported in the movie. The incoming asteroid has the size of Texas and travels with 22,000 miles per hour. The team of drillers lands on the asteroid when the asteroid reaches the moon, and they need 8 hours to drill a hole 800 feet deep. The nuclear bomb is planted in the hole and detonated exactly at the time barrier to separate the asteroid in two fragments, which, we are told, miss Earth by 400 miles. Although the movie refers to Texas for the size of the asteroid, it provides no exact measurements. Hence, we will convert the qualitative statement to a number. The area of Texas is 691,027 square kilometers. If this area is assigned to a square, this would give a length of 831 kilometers for the side of the square. In reality, Texas is stretching 1,244 kilometers from east to west and 1,289 kilometers from north to south. However, this does not modify the order of magnitude of the asteroid size. Both arguments give 1,000 kilometers. Only 16 asteroids have diameters 240 kilometers or greater, and only asteroid Ceres is of the previous size. Ceres has a diameter of 939 kilometers, but it is not in collision course with Earth. There is no extensive literature for the density of the asteroids. Only for some of them, densities have been investigated. For most asteroids, the value of their density is an educated guesswork. The most assumed value is 2,000 kilograms per cubic meter. Therefore, the order of magnitude for the mass of Armageddon's asteroid is 2 times 10 to the power of 21. We will also assume that, after the detonation of the nuclear bomb, the asteroid breaks in 2 fragments of equal mass. This means that each fragment has a mass of 10 to the power of 21 kilograms. Before the detonation, the asteroid is moving towards Earth with a speed of 22,000 miles per hour. We will also assume that the bomb has been planted such that all forces of the explosion appear in the perpendicular direction of the velocity. Therefore, in the forward direction, the fragments continue to move with the same speed. However, after the explosion, they have been given an impulse along the perpendicular direction as desired. Let E stand for the energy delivered by the explosion. To simplify the calculation and also give an advantage to the scriptwriter, our assumption will be that no energy from the nuclear bomb was spent for the splitting of the asteroid to 2 fragments. Then, E is equal to the yield of the bomb. The Hiroshima bomb was equivalent to 13 to 16 kilotons of TNT. Today, a modern nuclear bomb is equivalent to 20 megatons of TNT. The nations with nuclear arsenal do not spend effort to increase the destructive power, as it is already immense. Instead, they focus on reducing the size of the bombs. The script does not provide the magnitude of the yield used in the movie. To be generous, let it be equivalent to 300 times a modern bomb. Given that 1 ton of TNT releases 4.2 times 10 to the power of 9 joules of energy, the released energy is 2 times 10 to the power of 19 joules. And assuming that the energy is distributed evenly among the 2 fragments, each of them receives 10 to the power of 19 joules. This energy becomes kinetic energy along the perpendicular direction. Hence, if v is the speed of the fragments along the perpendicular direction, then kinetic energy equals 1/2 times mass times speed squared, which gives a result for the speed v of 0.14 meters per square second. Finally, we must estimate how long time the fragments travel before they reach Earth. The distance between Earth and the Moon is about 240,000 miles. Hence, once the asteroid has reached the Moon, it will take only 10.9 hours to reach Earth. According to the movie, landing to the asteroid will be attempted at this point, and it will take about 8 hours to drill. Unfortunately, unexpected delays occur during the drilling. It seems quite natural to assume that the detonation will occur about 2 hours before the fatal collision with Earth. However, I will better the odds, and I will assume a lead time of 3 hours or 10,800 seconds. We can now compute the deflection of the fragments by multiplying their speed by the duration of the motion. During this time, each fragment has deflected by a distance of just 1.5 kilometers. Earth's radius is 6,500 kilometers. To this, we may add the thickness of the atmosphere, but it is not really necessary. Comparing Earth's radius with the deflection of the fragments, we understand that NASA's plan is laughable. Instead of a single asteroid collision, NASA creates 2 asteroids which both collide with Earth just 3 kilometers away from each other. Besides the major failure described by the Fermi problem we solved, the movie suffers from many other scientific inaccuracies and errors. In a longer video, a Fermi problem discussing walking on the asteroid is added. And with this, we have concluded today's video. I hope you liked this cinematographic Fermi problem. If you did, please subscribe to my channel to help the creation of more content like this. Thanks a lot for your support.